Okay, so I'm going to begin by going through PVRTune. So all I need to do is click Start PVRTune Profile, and immediately I get this dialog asking me what applications do I actually want profiling information to be captured. So in this case I'm going to select all applications. So now every single GPU task coming into this device is being profiled. So to connect to this profiling server on the device, all I need to do is open up PVRTune and click Android USB device. All the profiling information is sent through ADB to this host machine. Now this is the screen we're greeted with the moment we connect to the device, and you can see that, well, there's lots of kind of different sections to it, but not much is happening at the moment. And that's because there aren't actually any GPU tasks coming into the device yet. But the moment I interact with the device, so I'm now going to go to the home screen, you'll see a flood of GPU tasks fill this center panel. So here we can see a whole load of GPU tasks and how long they took. So again, I'm going to start the GLES2 water demo. And I'm now going to go through this application to kind of quickly explain and try to understand what are the bottlenecks for this application. Now, when we start PVRTune, it is this center panel that is initially the most important. It lets us get an overview of how the application is running as a whole. But what do all these different sections mean? We've got 2D, renderer, tiler, and also a thread ID. Now, this thread section is here because we've got PVRTrace installed, which gives us access to the actual API timing data, so how long API calls are taking. So if you don't have PVRTrace installed, you'll actually be missing this bottom block. But for most purposes, you can actually understand most of what you need to know just from these middle two blocks. So let's zoom in and actually get a better understanding of what's happening in this task. So we can see there's a whole load of timing blocks here. So let's zoom in on this one. Okay, so if I highlight any one block, PVRTune immediately continues to show me all the tasks that are connected to rendering that particular frame. So as I go through different blocks, it's highlighting all the tasks that had to be run to create this frame. We can see on the bottom blocks when the actual API calls for this frame were made, on the tiler block above when the tiling work was done, and then finally when the actual rendering work was done. So obviously the timing data is obvious. This is where we're submitting API calls, but what are tiler, renderer, and 2D? Well, in a more traditional renderer, tiler can be thought of as the vertex processing. So this is where we've been given a stream of triangles to draw, and then we're simply doing things like performing transform on them, so running vertex shaders, and also culling unnecessary geometry, so doing things like backface culling. And then once that occurs, because we're a tile-based deferred renderer, we then also perform the so-called tiling task for the scene, which is where we bin every triangle into a particular tile on the scene to gain a really nice performance increase. So what can we immediately tell from this render scene? Well, the first thing to notice is that there's actually 3 tiler tasks and there's 3 renderer tasks. Now in a tile-based deferred renderer, we basically receive all the geometry for an entire render pass, and only once we've received all the triangles for render pass do we finally run our so-called vertex processing. So that means we know that there must be at least 3 render passes here because we've got 3 tiler tasks in this case. And that also follows through because we then have 3 renderer tasks. So can we make some sense of this? Well, the first thing to notice is that in this demo it's a water demo, and so what actually happens is for the first part of the render it kind of renders the scene from the perspective of below the water. It then renders the scene from above the water, and then finally it renders the main frame where it draws the whole scene, and this nice water effect is created by performing like a water shader runs based on the 2 previous render passes. So we can actually see this inside the timing blocks. So for this particular render, we can see that there's 2 short rendering blocks. So these are our this is the pixel shading phase. So renderer is, we've done our vertex transformation, and then the renderer is actually when we're running pixel shaders and rasterizing the scene itself. So we can see we've got these first 2 tasks. So we can think of this as it's rendering below the water, above the water, and then it finally renders the complete scene. And we can see that, you know, the below the water is taking 1.6 milliseconds, then 1.5, and then finally 11 milliseconds to draw the scene. It's the full screen scene. So these are different sizes because we actually render below and above the water at much lower resolutions and then do a high resolution final pass for the screen. Now you can see that this is taking 11 milliseconds, 1.5, and 1.5 milliseconds roughly again. Whereas the tiler task to do these scenes are actually a lot smaller. We're looking at just 3-4 millisecond tasks. They're taking a much smaller proportion of time to process. So that can immediately tell us that, you know, if we are GPU limited in running this application, we don't need to look at vertex processing or the amount of triangles that are coming in, because they're taking a very small amount of time to process. And what we need to focus on is things like pixel shading and texture reads, and try and understand why this task is taking 11 milliseconds to complete. So a bit more about the blocks themselves, and to try and understand, you know, what is the kind of color coding scheme here. Well, it's quite simple really. The top color indicates what process has generated these tasks. So in this case we've got a kind of magnolia purple color, and that's telling us that, you know, anything with this top color is from the OGLES2 water task. So we kind of need this because on something like Android we've got a lot of other processors running. Sometimes the compositor has to run as a proper graphics renderer. Sometimes we might have something like another application running, overlaying some extra information in the top right, or we might need to run a GPU task to draw this bottom bar. So let's just quickly identify, you know, have we got interaction with other things happening in the system that we need to watch out for. The middle color then indicates what frame number we're currently rendering. You can see that for these 3 rendering tasks and 3 tiler tasks, there's a kind of light brown color, and that indicates that all these tasks are for the same particular frame. They're all for frame 3431, and you can see that follows in the next task for 3432. They're this kind of light purple color again. And then the bottom color indicates what render target it's going to draw to. You can think of this as, you know, what frame buffer is it going to draw to. The first 2 tasks are drawing to frame buffer objects, and the final one is actually drawing to the screen. In most cases this is going to be double buffered, so what you'll notice is as the application is running, you'd expect it to keep flipping between these kind of same 2 buffers all the time. So what are the kind of first things we'd look for with this timing data? Well, the first thing we can tell obviously is that it's renderer task bound. That is the majority of our time being taken up. Now a lot of the time the first thing we find is actually that most graphical applications tend to be CPU processing limited, and it can be very easy to quickly find that out. Basically, either if we have the API timing data, we'll see a huge amount of kind of API calls happening, and swap buffers will only be slept for quite a small amount of time. Another quick way to determine if CPU load is an issue is on the left hand side. If we click on the monitor widget, we get a kind of rough summary of, you know, what is this GPU workload, and we can see it kind of tells us what we saw in the blocks, which is that we're not spending that much time on the tiler, and most of the time we're actually spending time in the renderer process, the pixel shading stage. But very importantly in here we also have the CPU load. Now in a lot of applications what we'll find is this is sky high, and when we're looking in this main screen there's actually a lot of time when the GPU is switched off and doing absolutely nothing. So in this case, in this screen we can see the GPU is quite busy, but let's say if I zoom out we can see a kind of strange glitch here. where this has gone a light shaded grey, that actually means the GPU is switched off entirely. And we can see below here that this swap buffers call has actually gone to sleep for 25 milliseconds. Now, in this case, it's probably got nothing to do with the application. This is a very simple demo running in a simple loop. But what we could suppose is maybe something in Android has happened, so maybe a garbage collection has been scheduled to run, and this kind of sleep and swap buffers has taken a bit longer than it ought to have. Now, in a CPU-bound application, we'll tend to see a lot of this, these big gaps where the GPU isn't doing anything at all. And in this case, we really need to focus on either maybe the API is being used in a way that's causing stalls on the hardware where it can't do any useful work because it's waiting for something on the CPU, or the CPU is simply too heavily loaded, it's making too many API calls, and we need to look at ways to reduce CPU usage. So the final block I've not really talked about is this is the 2D block at the top. Now you can see there aren't any really 2D tasks coming in on this render. What 2D tasks tend to be used for is actually the uploading of textures, or sometimes the copying of buffers, doing rotations, or performing what's called a swizzle on textures. Now you tend to only expect to see 2D tasks right at the beginning of a render. I'll see if I can find some. Right, so just before the demo's running, we can see we've got these quite small little 2D tasks running. This is actually basically when textures are being uploaded for this demo. So because the scene's not changing very much, we're not getting new textures, you're not going to see many 2D tasks. And it's really quite rare for kind of 2D texture uploads to be a performance issue. Okay, so what do we do once we've actually determined, in this case, that most of our bottleneck is due to the time to run the renderer? Well, this is the point where we'll start to look at the kind of more advanced counters. On this left-hand side, we've got a whole bunch of advanced counters from the GPU itself telling us important information. Now, if we take a counter, we can basically graph it at any point for what's currently happening. So if I drag this counter onto the main screen, we've now got a nice graphical view of it. One thing to note is this bottom left smoothing factor. A lot of the noise, a lot of the data coming from the GPU is going to be quite noisy. Tasks are switching on and off all the time. So if we bring the smoothing up and down, we can kind of see the more kind of accurate view of what's happening. So what you can actually tell from this counter is it is a 0 or 1 counter. So it's worth always watching this smoothing value when you're putting counters on. So let's take a counter like shader processing load. This is a really useful counter when we're trying to determine what's happening on the GPU. If I drag this on here, you can see the various different load levels on the ALU core as it's running. Now, what can we understand from shader processing load, and why would we use it in this case? Well, when a shader is actually running, there's a whole bunch of factors that might cause it to slow down. So what shader processing load means is, whilst the GPU is running, what percentage of time can it actually run useful instructions, so say multiplications or shader samples, or actually writing output pixels. So what this is telling us is, whilst the shader is running the renderer phase, we're only at, say, 56.1% shader processing load. And that means only half the time the GPU is capable of doing useful work. The rest of the time something is causing a stall, is slowing it down. Now, the kind of things that can cause stalls are texture reads, or some kind of external memory access, or maybe, in another case, there's so much geometry data coming through the renderer that it's having to rasterize so many triangles that it's not emitting enough tasks to keep the ALU core busy. So these counters let us quickly figure out, what is the cause of, firstly, shader processing load being low. But conversely, if shader processing load was very high, this actually gives us quite a simple optimization piece of advice, which is that if you optimize the pixel shader itself, you quickly see a big speed up. Now, it's quite typical on mobile applications to be bound by things like texture reads. The memory buses tend to be a lot slower than what people are accustomed to on, say, desktop class GPUs. So if we see something like shader processing load being, say, at 50% or lower, we then want to determine is, Is this because of, say, rasterization of triangles? There's just tons of triangles making it past vertex processing, and now the rasterizer's having to throw away a huge amount. Or is this because of external things like texture reads? So as we come down this list of counters, we're kind of looking for counters that will tell us useful things like that. So when it comes to textures, we've got a special texturing section. We've got texture overload and texturing load. And these give us kind of two counters to tell us whether the texture hardware is actually causing stalls for the main ALU processing hardware. In this case, you can see texture overload and texturing load are actually quite high. In this view counter, you can see for this particular section, they're at 27 and 87% respectively. So we can kind of tell that in this application, we're kind of bound by how quickly we can read textures. And that does make quite a lot of sense because we've got two render passes here which are then read as textures afterwards. So we're going to be doing quite a bit of reading back and forth from memory. So what other counters can be useful in different use cases? So in this case, it's just by looking at shader processing load and then at the texture counters, we've quickly figured out that in this application we are kind of bound by texture read speeds and the bandwidth of the system, and that's our main performance bottleneck. But what other kind of cases could we see? Well, if texturing load was fine, it was still at 0%, but shader processing load was still quite low, we might want to look at something like HSR efficiency. Maybe we've got a huge amount of triangles coming in that have made it past vertex processing, which means they didn't get culled, but they still need to be rasterized. If HSR efficiency is, say, really quite high, basically that means that a huge amount of triangles being submitted don't need to be drawn, and maybe we could do a better job of culling them before they make it into the hardware. So this brings me back to kind of our counters which give us a general overview of what's happening on the GPU. Renderer active is kind of giving us this information we got by looking at the timing blocks, which is that most of the time the renderer is the actively running component. But equally we've got a nice counter for tiler active and 2D active. So let's imagine that instead of the renderer task being the longest blocks here, that actually the tiler active task was the longest block. This would mean we're spending a huge amount of time processing triangle data. In that case, we'd look inside the tiler group, which gives us counters that can help us understand the workload that's coming in. So here we've got this counter triangle. This is telling us of all the triangles submitted for the vertex processing phase, what percentage of them were culled or thrown away. Now, if we had a really high tiler load and the triangle cull rate was really high, like 80-90%, then we immediately know, okay, we can do a better job on how we're submitting geometry, and maybe we can reduce the amount of triangles we're submitting into the pipeline. So say we had the case where shader processing load was extremely high. We can then come into something like cycles per pixel and get an idea of how many cycles a particular shader is taking. Or in some cases we might find that something like register overload is particularly high. This indicates that there's been a lot of kind of register pressure to run a particular shader and that we've had to spill to external memory. And finally we get to the kind of bottom section of counters. These only happen when we've got PVRTrace installed, and they tell us lots of useful things about the actual draw calls. So things like how many triangles were submitted for a draw call, how many scissors, were any textures modified. These are all things that can really hurt performance on a device. So once we've got an idea for what might be causing a bottleneck on the GPU, if we've got PVRTrace installed, we can actually use another feature called render state overrides to kind of quickly determine where the major issues are. So what these are kind of the most common cases that are going to be hurting performance a lot. So the first one is maybe something like maybe your screen has a huge amount of blending. Now blending can be very expensive if each layer needs to read from a texture. So what you can do is just quickly click disable blending, and straight away you can see that in this scene live we've disabled blending. You can see that the text here is now not blended with the scene, and in certain applications this can quickly help you see where you're doing more blending than necessary. Now again, if we're finding we're completely texture load bound, we can choose to override all our textures with small 2x2 textures. We just click force 2x2 textures, and immediately on the device you can see all these textures are now much smaller, and we should immediately see a big speed up on the device. So what we're kind of doing with these, by toggling these different render states, is we can quickly figure out, okay, if I do force 2x2 textures and it doesn't get any quicker, then I know that it's either my fragment shader is maybe too heavy on ALU usage, or maybe I'm actually bound on just the amount of geometry that's coming in, like there's too much geometry to rasterize, or there's too much geometry to vertex process. So it's very quick at kind of helping you eliminate what things might be the bottleneck. So for example, if I click force flat color shader, this is going to get rid of everything. It's going to get rid of texture reads. We'll just be performing a very simple writing out with a single color. And again, this helps us successfully kind of separate what is processing vertex work from doing fragment work. And so we've got other options in the same vein. So we've got disable stencil test, disable depth test, scissors. We also have disable flush and finish. This can be quite useful, especially on some of our older drivers. So flush and finish behavior are actually quite driver specific, and finish in particular is a very expensive call. Because we are a deferred architecture, we actually want to queue up as much work as possible all the time, at least kind of a frame ahead. And I'll go into that in more detail shortly. But if you call GL finish, that's basically saying everything that's been submitted so far, I want you to render all of that and only come back once it's actually finished. Now this is very expensive for our architecture. So what you can do is choose to disable these finish calls, and equally flush essentially means, okay, all the work I've queued so far, I want you to start working on that. And again, this can be quite expensive, or might have kind of performance implications that mean we end up drawing more buffers than you might have thought or intended to. So again, this is very useful to kind of disable flush and finish calls. Then we have disable texture modifications. Again, modifying textures is something that kind of either has a cost in what we call ghosting the texture, which means we make a copy of it so that whilst the GPU is still using that texture, we make a copy and change a new version of it, or we simply have to wait for the GPU to finish using that texture before we change it. And finally we have disabling texture filtering. Maybe you've got a very expensive filtering mode on, and then disable discard / alpha test. Again, these are things that can be quite expensive to perform on really on any graphics architecture. And then finally, disable frame buffer accesses. These are things like calling GL read pixels, which really do stall the whole pipeline. So with this kind of set of render state overrides, you can quickly determine where you're losing the most bandwidth. Now I'm more about what do I mean when I say something like finish can really slow down the GPU by making us wait until an actual task is finished. Well, in a deferred renderer, to perform optimally, we always want to get into this use case, which we can see here. What's happening here is, if we zoom out, you can see that the rendering task for our current frame is performed at the same time as the tiling task for the next frame. Now this is really important for performance reasons, and it's why being a deferred architecture is kind of so useful for performance. What this means is, by overlaying vertex processing work for the next frame with rendering work for the current frame, these two tasks have very different performance characteristics. Kind of fragment processing work might read a lot of textures, in which case it's going to go to external memory a lot, whereas vertex processing work might not have as kind of heavy bandwidth requirements. So by scheduling these two tasks at the same time, they can both, firstly, we're just generating a lot more tasks on the ALU, which allows us to hide latency much more effectively from external memory accesses. So what I'm really saying with this is, when you run your application, you want to ensure that you're getting into this state. It's something that we call render ahead. What it means is that we're always, from the API point of view, we're actually we're doing our rendering work kind of a frame behind, but the truth is we're submitting the work a frame ahead all the time. So we're always kind of, from the first frame, we'll immediately kick off work to render 2 frames straight away, which means from that point on we're always processing the tiling work for the frame ahead whilst we perform the rendering work for the current frame. And this is very efficient for the architecture, and it's something, if you don't see this behavior where we've got this kind of tiling work happening ahead of time whilst the previous rendering work happens, then you really need to kind of look at your API calls and try and understand, why isn't the application going into a render ahead. The last thing for me to mention is, on the bottom right we also have the process ID list. So this is just telling us what particular color and process ID and what the process is. So in this case we can see process 3 is OGLES2 water. Okay, and one final feature is that we can search using this find view and maybe look for particular calls or tasks, or just highlight one particular process. Now hopefully this gave you a quick understanding of how PVRTune works and how to use it to analyze performance. Now what you can see with PVRTune is it proposed a lot of questions. So why is the shader taking so much time? Why are these textures maybe so expensive to read in memory? Lots of questions about why are we having to do these things? Now PVRTrace is kind of the answer to this. Trace provides all the answers to these kind of questions. So in the next video we're going to go through how to use PVRTrace to actually understand the application itself and begin to make changes to the application that will improve performance.